let us start. Okay, so I hope so that I am visible to everyone, and here also live. Yes, we are live. Okay, good evening everyone. This is Ashank David. Welcome back to Coda's Arcade. This is your 24th session of our DSA for Placement Series Live, and in today's session we are going to talk about AVL trees. Now in the yesterday's class, as we have already know that we are doing the whole trees concept from past so many days in so many sessions. I have completed binary trees, I have completed binary search tree. Yesterday I have completed display trees. So if you haven't watched any of those sessions, I would suggest you to go ahead and watch those sessions as well. In today's session, we are going to do the AVL trees, where I will be explaining you about how AVL trees works and what are the things that you need to take care of in AVL trees. Right guys, so well, before I start with this, I would like to request you people to please like, share and subscribe to our channel Coda's Arcade, and don't forget to press the bell icon also, so that you won't miss any future update. So also I also make sure to share this live stream as much as possible, so that you guys can share this live stream as so much, so that those people who are learning DSA for the first time and they want it all for free, they can also learn it from these live sessions. Now let's start guys, without any further ado. Sanjana Singh, present from GIT. Hi Sanjana from GIT College. Welcome to our channel. I hope so that you are learning from our today's concepts, and in today's class we are actually gonna learn about AVL trees. So let us talk about AVL. I hope so my voice is also audible and I am also visible. If you have any problem related to camera or audio, please do let me know in the comment section. And I hope so. I am checking the audio. Audio is correct. Audio is fine. I can see, I can hear, I can see the bars going up and down. But yeah, audio is working. Camera is also fine. I hope so that you are able to see the font which I have kept here. If you have any problems or doubts, you please do let me know in the chat. I can read your chats. There's a screen in front of me, right? Alright guys, so let us start without any further ado, and please do share this live stream. Now today we are gonna do AVL trees, and the code which you are seeing just behind me is the code for AVL guys. And here let us understand first how AVL tree works. Okay. So yesterday we have learnt about display trees, where we have understood that the most recently accessed node is kept on the top of the tree or the root of the tree. But in this case, when we are talking about AVL trees, we are talking about a tree which can self-balance itself. So if I want to explain about this, I can say self-balancing tree is a AVL tree. Okay guys, I hope so that this is very much clear. So self-balancing tree is also called as AVL trees. Okay guys, I hope so that this is very much clear. What is now self-balancing? Let us understand about self-balancing. Okay, what is self-balancing? Now you might get, before I start with this self-balancing, what is the full form of AVL? Okay, what is the full form of AVL? It is Adelson, Velsky and Landis tree. Adelson, Velsky and Landis tree. There were three people, Adelson, Velsky and Landis. These three people actually invented the concept of AVL tree, and hence the name came AVL. Okay, so these are the three people who developed this tree. So basically they said that the tree should be self-balancing. Now what is the concept of self-balancing? Let us understand about that. So here we are talking about self-balancing. Here the word self-balance means the differences between the left and the right subtree, is automatically set to 1 or -1, in between. Actually the idea is between 1 or -1. Okay, what is this? Let us understand. What I am trying to say here is, imagine, quickly imagine, I have a binary search tree. Let's say this is 100, this is okay, let's not take the same example. Let us take the same example. 100, 50, it is 50, 50. On the right hand side, let us 150. Is it self balanced? Let us not talk about self balancing. Is it balanced? Yes, this is balanced. See the height of the left subtree and the right subtree. This is the right subtree. Right subtree height comes up to 1 because we have only one node on the right subtree. On the right subtree we have only one node, so the height comes up to 1 for the left subtree. Okay. Then if we talk about this on the left hand side, on the left subtree there is one node. On the where? Left subtree. On the left subtree. So you can see that both the places there is 1 and 1 here. That means the tree is balanced. Okay. The difference between the heights should not come up more than 1 or more than -1 or lesser than -1. I hope so that this is very much clear. It will be in between -1 and 1 should come, or maybe 0 should come. So what is the difference here? 1 minus 1, 0. So 0 is coming. That means the tree is balanced. I hope so that this is very much clear to all of you. Understood? Now if I said add, I am going to add 30 here. Now is the tree balanced? Let us calculate. Here now the height of the left subtree is 2 and here the height of right subtree is 1. Is it balanced? 2 minus 1, 1. Yes, it is balanced. I hope so that this is very much clear. Still it is balanced because the differences between the two heights on the true left subtree is 1. Mahesh, hi sir, hello Mahesh. Let us continue. Okay. So now if I say I will add 170 right here. Is the tree balanced? Of course it is balanced because the left subtree and the right subtree height of anyone's height is equivalent. If I say here add 70, is it balanced? Yes, it is still balanced. Here we are not talking about the number of nodes to be exact. Here we are talking about the depth of the number of nodes in this case, which means the height of any branch inside the tree, and that is why it is called as balanced. Okay. Hello. And the camera went off and I need to start it again, guys. So there we go, we are back again. Okay. So now let us see if on the right hand side, on the left hand side here, on the right left we have, let's say 130. In this case Is the tree balanced? Is the tree balanced? Yes, the tree is still balanced. Okay. So in this case, if I say, because you see the height of all the trees are what? It is the same. Understood my point? But in this case, let us say, I add one more. If I say add 10, now is the tree balanced? No, the tree is not balanced now. Why? What is the height? 1, 2, 3 is the height of the left subtree. And what is the height? Okay, this is still balanced, yes, it is still balanced here. But what if I had no node here? Let's say there is no node here, okay, in this side. Now is the tree balanced? No, now the tree is not balanced. Why? Because you see 3 minus 1, it is coming 2, which is greater than 1. In this case, this is not balanced. So what is AVL tree? AVL tree is a self-balancing tree. Means when I do any insertion, if the tree balance is imbalanced, if the tree is imbalanced while doing insertion, if the tree gets imbalanced, then it automatically balances itself. And this is what you call as Adelson, Welski's and Landis tree. This is AVL tree or Adelson, Welski's and Landis tree. These are the 3 people who developed this tree, a tree which can balance in itself, on itself automatically. This is what you call as self-balancing tree. In this case, AVL tree is a type of a self-balancing tree. Now, self-balancing tree is just the concept. There are many other types of trees also which can self-balance, but those are different kinds of tree. But this is AVL tree, we are trying to do it directly self-balancing tree. I hope so that this is very much clear. So this is gonna be your self-balancing tree. Got it, guys? I hope so that this is very much clear. Understood? So now, in this case, let's take a smaller example for in this case. Let's take a smaller example. Let us say I have 10. And now I said add, let us say add 20 here. So I added 20. Is the tree balanced? Yes, it is balanced. Yes, it is balanced. If I say add 30 now, so 30 will be added here. Now the tree is balanced? No, now the tree is imbalanced. Why? Because the height of the right subtree is 2 while height of the left subtree is 0. So 3 minus 0, it is 3. Or 0 minus 3, it is minus 3. In this case, the whatever you do, the index is coming, so this is actually 2. So 2 minus 0 or 0 minus 2, it will come as minus 2, not minus 3. So that becomes the height is imbalanced. I told you, if it is between 1 and minus 1, then only it becomes balanced. Understood my point? But in this case, it is imbalanced. So what we need to do in this case, now listen to this very carefully, guys. I am saying this again, because now here we are added this into right. So that means we need to do left rotation. In this case, to balance this tree, we need to do left rotation. We need to do left rotation of 10. Understand a point? Left rotation of 10 means the root in this case. So how will it work? How will it work? It will work like this now. It will work like this now. This will be changed to further. This whole thing will be changed to what? It will now be changed to 20, 10 and 30. This is what you called as left rotation. I hope so that this is very much clear to all of you. Clear? My voice is audible, and I hope so that this is very much clear. Okay, but my face is coming a little bit blur, I believe, right? Shall we adjust it a little bit? Better? I feel so it is a little bit better now. Okay. The screen is visible though, right? The screen is also visible. Okay. So now this is called as left rotation. So I said left rotation. This is the left rotation. Left rotation. This is scenario number 1. Okay. Now let us say in scenario number 2, you had 10. Okay. You had 10. Let's say you have 30. 30. You had 30. Now you said add 20. I added 20. Now you said add. Now you said add. Let's say you add 10. In this case, I added 10. So 10 will go right here. 10 will go right here in this case. But actually, it will be this side. No, 20 will be added right here. You got my point? 20 will be added right here. And if I say 10 here, then 10 will be added in this case. So this time it is going onto the left hand side subtree. So in this case, what happens? The right rotation will be done. The right rotation of root will be done. The right rotation of root will be done. Okay, in this case, what happens is now 30 will go on the right and 20 will come up right here, and here 10 will come again and 30 will be coming right here. I hope so that this is very much clear. Sir, you said height difference is in between 1 and -1. Not -1, 1 and positive 1 and -1. Positive 1 and -1. For example, check here, check this out. This is the root node. This is what? This is root. I said root. What is on the root's left hand subtree? On the roots, Mahesh, see this. See this. On the root's left hand, how many nodes are there? 2 nodes are there. So the height of the left subtree becomes 2. Height of the left subtree becomes 2. Correct? The height of the left subtree is 2. What is the height of the right subtree? It is 0, because there is no nodes. Correct, Mahesh? Correct. Now 2, do 2 this time. 2 minus 0. 2 minus 0. How much? 2. 2 is greater than 1. And our range should be -1 to +1. Did you get, Mahesh? Reply please. Did you get this? I hope so that you got this, what I am trying to say. Okay. -1 to 1 should be the range, not lesser than -1 and not greater than 1. Lesser than -1 means it cannot go into -2, -3, -4, -5, cannot go like that. Okay, Mahesh? The concept is very simple. Subtract the height of the left subtree with right or right with left, no worries. The difference should not come more than 1 and lesser than -1. Clear? Whenever you are getting like that, that is a imbalanced tree. Okay? And our AVL tree is self-balancing, means automatically it will balance the height. I'm explaining the logic yet. Okay? So here, in this case, you see, root's right height is 2. 2. Root's right height is 2. Root's left height is 0. So 0 minus 2, -2. In this case, -2 is even smaller than -1, which is imbalanced. Understand our point? Imbalance. So we will do left rotation. When the right height is more, we do left rotation of root. In this case, 10 will go down, 10 will go down, 20 will go up. Maintaining the BST, it's a binary search tree. Got my point, guys? Binary search tree is important here to understand. Everything is mostly a binary search tree. You say splay tree or you say AVL tree, it is all binary search tree only. Clear? I hope so that this is very much clear to everyone, guys. Okay. So we will do left rotation in this case. But in this case, our left subtree height was more. Then we will do right rotation. Clear? This is very much clear to all of you. Okay. Now, third scenario. Take out third scenario. Third scenario is what we can do is let us take 50 as the new root. 50 as the new root, and I have 70 on the right hand side subtree. On the right hand side subtree, and I said we have 60 right here, 60 right here, 60 right here. In this case, you see that the tree is imbalanced because the height on the right subtree is 2 while height on the left subtree is 0. Height of the left subtree is 0. In the above case, height of right subtree is 2. Why? Because it is 50s, 70 and 60. This is 1, this is 2. So here height is coming as 2, correct? Height is coming as 2. And when the height is coming at 2, but on its left, the height is coming as 0. We saw that there is no height. Understood? So in that case, what is the difference here? So say 0 minus 2 equals to minus 2, which means it is imbalanced, or in simple language you will say not balanced. Clear? I hope so that this is very much clear. So this tree is also not balanced. So in this case, what we will do? In this case, we will say right, left, rotation, right, left, rotation. I hope so that this is very much clear. In this case, what we will do? We will do right, left, rotation. Okay, guys. 1 second, guys. Okay, so in this case, what will happen now? 70 will come right up there, this will go down up there in this case, and this will be set into this. This is how it will be done. Clear now, guys? So this is how it will be done, and these rotation will be done. And then the vice versa. Maybe on the left hand subtree of this can be it like that. Understood? So fourth scenario can be, let's say we have 50, and on the left hand side we have 30, on the right hand side we have 40. The height is 2, but on the right subtree it is 0. So again we need to do rotation. So in this case, the tree will be rotated back to 30 and then 50 and then 40. Wait. This will become left right rotation. This was right left rotation, okay, but this will become left right rotation in this case. Left right rotation. In this case, what will happen? 40 will come up, 50 will go here, and 30 will go right here. I hope so that this logic is very much clear to everyone. Okay. So, this is how you will do, and these are the cases that we will be handling in the code. Okay guys. So, there will be left rotation, right rotation, left right rotation, right left rotation, and the insert function and the AVL self balancing function. We will create get height and we will create is balanced or not function. Okay guys. So, let us move on to the code, and this is the code guys for it. So, let us understand. So, here the code is very classic, the same classic code we have written. So, in this case again the BST implementation exactly the same. We have imported queues we have used the queues here for what? We have used the queues for BFS, breadth first search traversal, and here we have created the node class where we have taken the key left, right. In this case just we have created a height. So, as soon as I insert the element, the height will be equals to 1. Understood our point for that node in that case. Got it guys? So, every time the height of that particular node will be 1. So, let us say I want to calculate the height. I can traverse down that particular the branch, and I can add all the heights to get the height of that subtree. I hope so that this is very much clear. So, the idea for writing height is the height of the new node is 1. So, as soon as the new node gets inserted, the height becomes 1 for that new node, and if I want to get the height, you see class AVL tree we have written private, and in the node star root we have discussed it. Of course, we are doing this from past so many days by now. Private section and public section of the class. In the private section we are writing the helper function, on the public section we are writing all the functions which are directly available to us in the main function. We are already doing that. I hope so. If you are the follower of this live stream, you must be getting the code of the style of the programming I am doing here, and you will be understanding it. So, if you are new here, please do subscribe and please do watch our previous live sessions guys. So, do not forget that as well. Understood? So, let us say I want to get the height. How will I get the height? So, I start from that particular node. If there is no node, then you will return 0, otherwise return the node height itself. You got my point? Understood this? So, that is how we will get it. And then if I want to see if it is balanced or not, okay. So, actually it is not balanced. Of course, whenever we will be doing an insert function, we will get it imbalanced. So, in this case we have right rotate, we have left rotate in this case, and this will do the job. Insert recursively function, you see how insert recursive function is working. We have node is equals to null pointer, and we are returning that if the normal BST insert function. We have added the comment also. If the root is lesser than the node's key, then go towards it left and insert the recursively thing and do the thing vice versa. Else, if the key is equals, then it is not allowed in the BST, because in BST of course duplicate values are not allowed, as we have discussed before. Understood? So, now this is the thing. We will update the height of the ancestor nodes. See, whenever you will add a new node, of course you need to add the 1 to that ancestor node, correct? Because let us say you have added one node, that is one root on the left hand side or the right hand side. Let us say this side is your new node added. So, the value of this new node will be 1. I mean to say is, for example, take this example only. This is the root. You added this 30. The height of this 30 will become 1. Understood? As soon as you add this one, the height of this node will become 1. But you don't have to worry about this, because you are just adding 1 in here. So, the height can be incremented of the particular node. So, every time you add the new node, that height from that new node is taken and added in the just the parent node of the left subtree of whichever node's height you want to check. Say suppose you want to check the height for this, then this height will be taken. I hope so that you are getting my point. So, that is the same thing which we are doing here. So, we are getting the height, node's height will update with one of maximum of get height function will call and will whichever is going to be maximum, okay, whichever is going to be maximum. See, node's height updates the height of the ancestor node, okay. The node height, that particular target's node height will be 1 plus the maximum of its height on its left, okay, and will call the height on the right hand side in this case also, okay. So, see, it might be possible that this is the node, this is right now balanced, okay, this is also the case where this is also balanced, only, okay. Now, let us say you want to get the height, you are getting the, now it is possible that there can be one node here or there can be one node here also. Are you getting my point? One node can be connected to this node or one node can be connected to this node. We don't know. So, for that we are taking the maximum of this and this subtree. Okay guys, what I am doing is maximum of this node and this node, whichever is maximum. We are maximum of get height of this node and get height of this node, which is going to be the height of the left subtree. Is this clear now guys? This logic is clear or not? I am audible, clearly audible, this is getting recorded. So, in later future sessions if you are getting confused, you rewind back and see what I just said right now. Understood my point? If you are not watching live and if you are watching in some future days and you are not able to ask me the doubt, rewind and listen to me very carefully guys. Understood my point, what I am trying to say? So, what I said is I want to get the height. Let us say I want to get the height of this node. I want to get the height of the left subtree. This is the root. I want to get the height. General. Is the tree balanced or not? I know that this is balanced, but how will computer get to know? I need to write the code, correct? So, very carefully observe here that if I want to get the height, I will get the height, how will I get? On the left subtree, let us say I will pass this left subtree's node, okay. So, I will say maximum of get the height of the left subtree and get the height of the right subtree. Are you getting what I have written? This is the place where you are standing. Take out the maximum of the left and maximum of the right subtree, okay. So, the height comes up to 2 and this height comes up to 1. What is the current maximum height? 2. So, 2 will be given out here. I hope so that this is very much clear. Okay, but can't we just run through the tree if the child node points towards null? We can just ignore the case and move on to the different branch or the child node till we reach the last node. 1 minute guys. Yeah, my camera went off. Madhukar Verma. Yes, of course we can do it, but how many times you will travel? Now Madhukar Verma, this is for you, okay. I am saying that, I am just asking you in this case, tell me what if you have a very big tree, a very large tree. Let us say there are hundreds of nodes in between, in below there. Your program will become very inefficient. because your program will be traveling into all hundreds of branches below there, doing traversal and will waste a lot of time in there, because then the time complexity will come as log of n. So, not log of n, sorry, n, O of n. In your case, yes, we can do it like that also. Madhukar Verma, yes, Madhukar Verma, we can do it like how you are saying, yes, we can do it, but that is going to be very inefficient. Ask me why? Why? Because that will be doing it in O of n time complexity, while mine will be doing it O of log n time complexity in this case. You got my point, Madhukar Verma? But yes, your method will also work fine. But the thing is that it will take a lot of time, because in your case you will be traveling the whole thing. And how do you travel? How do you travel? If you are doing BS, not BFS, BFS is not feasible here. Let us say if you are doing DFS, then you will apply recursion, and you know, as soon as you apply recursion, it will keep on going. Suppose it is a very big tree, your recursion will never stop, and you will get time limit exceeded, TLE error into your machine. Yes? Yes, Madhukar Verma? Agreed. Understood, sir. Very good. So, that is the case. So, why don't you do one thing? Why to travel? You don't have to travel. Every time you add a new node, the ancestor nodes will be +1. In this case, when you want to get a height, you don't have to travel. You just directly take it from the ancestor node. Why to go down the whole branch of trees? Well, you can just get it from the ancestor nodes. I hope so that this is very much clear. This will save a lot of time and will save a lot of energy also, will save a lot of process also, and will save a lot of memory or space also. So, time and space, both the complexities are also met. Well, okay guys, apart from that, this is how you get the height, okay, you will update the height, okay. So, get the height, you will check if the nodes are balanced or not. So, get balance is the function which we have written up there, okay. So, get balance, how the balance is measured, okay. See, if not of node return 0, means if there is no node, return 0, if the node is null, then return balance as 0, there is no node only. If the left height will get height, int left height, get height of node of left. So, this will give me the get height. Height will be calculated like this. Height will be calculated like this. We have written the height function also, no, right here, there is this. Okay, we will get the height from that left subtree and we will get the height in the right subtree. In this case, we are just directly getting the node's height. You might be thinking that it will be returning 1, but actually it will not return 1. As soon as the insertion had happened, we had already updated the height in this case. So, this way the height of the ancestor will be taken and that will be returned as soon as possible in this case. Are you getting my point? So, in this case we will be returning that. So for example, you have let us say done around, let us say create a height of, let us say 2 by 2, okay. So, height 2 will be updated already in the ancestor node. So, you can just get it directly by just returning that node's left height. Understood my point? So, that is why this function is just returning nodes of height. It will not return 1, but it will be already updated from the insertion below, before only. Understood my point? That is the case. Apart from this, so we got the height, left height, we got the right height, and we are checking if the left height minus right height is returned or not. Okay, we are returning the height. So, as soon as I returned the height, where it goes? It goes right here, balance. Now, we are checking if the balance is greater than 1 and the key is smaller than the node's left key. That means we will have to rotate at right. Understood my point? What I have done? Understood this, guys? balance, if the balance is greater than 0, sorry, if the balance is greater than 1, if the balance is greater than 1, means it is, what did I tell you? If the balance is coming as more than 1, then it is not balanced. So, in this case, if it is not balanced and the key is smaller than, if the key is smaller than node's left key, that means it is left version, that means it is this case, that means it is this case, case number 1, not case number 1, case number 2, right, this case. Check if the balance is greater than or lesser than 1, whatever it is, and the key is smaller than left, root's left key. Understood a point? Key is greater than 1 or key is smaller than node's left key. Key is smaller than node's left key. You need to do right rotation. Understood my point? You need to do right rotation. So, here you are returning right rotate. Rotate rights. There you go. I hope so you guys are getting my point, what I am trying to say. Reply yes or no in the chat. I hope so you are getting my point or not. Okay, reply please. Otherwise, I will not get to know are you getting it or not. Okay. So, how are we doing right rotate? Of course, we need to perform right. We called that right rotate and the right rotation was done in this case. Okay. So, we took, let us say we want to rotate the right. Okay. So, we will take that particular node and we will store it into x. Whatever x is, y's left will be stored there and t2 temporary 2 here we are taking as x right. Okay. Say for example, let us mark this code and understand this beautifully. Okay. Let us properly understand this. Okay. So, I said that there is this situation happening where this is 30, this is 20 and this is 10 for example. Okay. And you said that do a right rotate. So, y's left is stored into this x, x is stored and y's x right is stored into this t2. Okay. In this case, right rotate is this in this case. Okay. If the right rotate is this. Okay. So, x is equals to y of left, x is equals to y of left, and in this case we are storing this as null. Okay. We are storing this as null. Yes, we will perform the right rotate in this case. So, we are storing that in here and then we said that x of right is equals to the y, which means this will come right here 30 guys. This is T2, guys, temporary 2 is storing what? Null in this case. Okay. And then I said x of right is equals to, you will come at that place. Understand our point? I hope so. And y of left will go right here. I hope so that this is very, very much clear. Now, don't worry about this. Okay, don't worry about this. The numbers here, I just wanted to explain you how it actually works in this case. So, basically how this is working is by swapping the elements. Don't get confused with the numbers. If I delete the numbers, then you will understand it in much more better way. Okay. So, the values are getting rotated like this and this is how the right rotation is working in this case. Majorly your right rotation is happening like this. I hope so that this is very much clear to all of you guys. Understood our point? Alright. So, this is how it is going to work in this case guys, and this is your right rotation, and then we will update the height. So, if I want to update the height, I will again get the maximum of the height and plus 1 I will update the height. I hope so that this is very much clear to all of you. My camera went off, let me just switch it on, back online, and then we will return it. The new root will be returned right there. Okay guys, understood this? So, that is how, and the same thing is what we are doing in the left rotate. In the left rotate also we are doing the same exact thing guys. The difference is that we are just doing left to right, right to left, that is it. the same code which you have written up there is gonna be written this make this left to right, then make this right to left, and that will work for all the cases. Well, I hope so that this is absolutely clear to what I am trying to say and explain you guys. Alright guys, that is how it is done. Okay, and then okay, you see left case, right case, left case and right case, all the cases are getting handled very easily. I hope so that this is very much clear. For you see left to right case, we are going to the left and then we are calling the left rotate and then we are doing the right rotate. Okay, so we have to actually write only left rotate and right rotate, but call them simultaneously so that the left right or right left rotate also happens. I know it is going to be a little bit confusing and in the beginning and the start, but don't worry guys, as the time passes and as you practice more and more, you will keep getting it. I hope so that this is very much clear. And for all the 4 conditions which we have discussed right over here, we have done all of them. So left, right, left and right, all the rotations are made. And I hope so that this is very much clear. Alright guys, that's how you will do the AVL tree concept. And once it is done, return the node. So any unchanged node pointer is gonna be returned in this case. And there you go, insertion will happen. Rest of the other things are same. DFS helper and DFS in order, pre-order, whatever it is, you have understood this really well. I hope so that this is very much clear. Rest of the code is exactly the same and we are just doing the inserts and we are just updating it. That's all about AVL trees guys. I will give the link and the same exact code. I will pin it in the comment section below, and also let us start our doubt session now. So if you guys have any doubts, please do let me know. I hope so that this is very much clear. The code is very similar to what we are writing. I am trying my level best to keep the codes as simple as possible and exactly the same as our coding style suits. That is how we have learned in BST. The same coding style has been used, and I hope so that this is very much clear. I can see the comments. There are no doubts here guys. If there are no doubts, we can end up the session, or if you have any doubts, please do ask me. I'll give the link of the blackboard, and I'll give the whole code in the comment section below. I'll pin it over there, and I'll give the link of the notes in the description box below. Alright guys. Well, if you have any doubts, please do let me know. That's all for today's class. 2 people are watching right now live. You can ask if you have any doubts. No doubts guys. I will be pinning this code also. This is all about AVL trees. Remember AVL trees, Adelson, Welskis and Landis-tree. These were the 3 people who designed this tree, and these were the 3 people who brought the concept of self-balancing tree. You have understood how the tree is balanced, what is height balancing, everything. Apart from it, split tree was a little bit different, but the concept was same. In the split tree, we were also doing the same logic of rotate, left, right, rotate only. In this case, we are doing left, right, rotate, the same thing which we have done in the yesterday's class, but here we are playing with the heights. So understanding if the tree is balanced or not, and based off of that, we are doing the job. Alright guys, I hope so that this is very much clear. That's all for this session guys. Do not forget to like, share and subscribe to our channel Coders Arcade, and don't forget to press the bell icon also so that you won't miss any future updates. Thank you guys so much for watching. For those people who watched this stream till the end, I thank you guys so much, and any doubts, please do let me know in the comment section below. I'll be ending up this session. Don't forget to follow us on Telegram and our Instagram channel. I hope so that I am live everywhere. So yeah, so don't forget to subscribe to our channel guys, and don't forget to stay tuned for more upcoming videos like this. Tomorrow let us do one more kind of a tree, red and black tree, or let us see if we are able to start some other concept, we will do that. Okay guys, I hope so. A lot of trees concept we have covered till now. Till now how many trees we have covered? BT, binary tree, binary search tree we have covered, split tree we have covered, and AVL trees also we have covered already in the course. So yes, let us continue tomorrow's class guys. Don't forget to follow us on the Telegram. The link of the notes, also the link with the video, I will be giving up in the Telegram session, and very soon I will be starting up the mock interview session also guys. So I will be putting up the link by tomorrow for the mock interview session. So those people who are interested in joining mock interviews with us, I will be putting up a link. Please do register for it. It is all for free, and if you are interested for having mock interviews with me, I will be your interviewer and you will be right in front of me. That too live on YouTube if you want, depending upon your choice. We can come live also on YouTube guys. So if you are ready for it, please do fill up the form for it, and please do let me know by tomorrow. And any updates regarding internships or placements or anything about course, I will be updating it on Telegram channel. So please do not forget to follow our Telegram channel also for all the updates, for the latest updates for our Coders Arcade. Okay guys, and if anybody wants to do any course, crash course on DSA, or even courses on other languages, or any other course on Java development even, we are open for it guys. So please do ping us, and the contact details is already given in the description below. You can contact us, and that's all guys. Thank you guys so much for watching. I will see you guys again tomorrow. Tomorrow's timing I will take it to, for example, I can take it at either 6 o'clock in the 6 p.m. in the evening, or 7 o'clock. Tomorrow morning I will schedule the live session. At that time you will see whatever the time is written, that time you can come and join us. Most probably it is going to be in tomorrow's evening only, either at 7 or at 6, depending upon the time that we have. Alright guys, thank you guys so much. I will be closing this live stream. I will see you guys tomorrow, same time, most probably same time, 7 o'clock Indian Standard Time, and that's all guys. Thank you guys. I will be switching off the live stream, and yep, I will see you tomorrow.